Okay, can we start?
Yes.
Okay, let's start. Today's speaker will start in this new semester with Maciej Ossowski, who will tell us about not solution, I guess, or not solution, or
Also, yeah.
or some solution.
Okay, so yeah, as the title suggests, I want to talk about something which is very much so motivated by the tau-NUT solutions, or just any solutions containing the NUT parameter, in particular about their axes and conicities, which I want to define. And in the end, the application will be a little bit broader than just the NUT solutions. So this talk is based on a joint work with Ivan Kolash and Paweł Ktoś from Charles University. And this is the debut of this work, so we expect the preprint to be available soon. So I want to talk about the axes in NUT spacetime, which are necessarily singular. So let me start with okay. Let me start with saying something about the regular axis, how the axis of rotation is usually defined in a spacetime, about the measure of the singularity of the axis, which is called the conicity and the corresponding conical singularity. Then I will tell you about what fails in the generic case, which will lead us to the new proposals for definitions of the singular axis and the conicity. And I will go through the examples which are most commonly associated with some kind of a string being present in the spacetime, being it a cosmic string, spinning cosmic string, or the string in symmetry, or the so-called Misner string in tau-NUT, or more broadly in all Plebański-Demiański spacetimes with the NUT parameter. So what is the regular axis? So to get the regular axis of rotation, or of some rotational symmetry, we probably first need to define what is a cyclic symmetry. And this is the standard notion that the cyclic symmetry is an isometry of a spacetime, such that this is an action of a circle, which is a Lie group on the spacetime manifold. And well, this angle is just the angle by which we rotate the spacetime. Then the axis is precisely the set of fixed points of this symmetry. This is easy to imagine. If you rotate a piece of paper, then there's only one place which doesn't rotate, it doesn't move. This is the axis of rotation. So it's more convenient, instead of talking about this isometry, it's more convenient to talk about the Koenig vector field that generates this symmetry. And throughout the whole presentation, I will be denoting it by C and calling it the cyclic Koenig vector field. So this Koenig vector field in the manifold, it generates this cyclic symmetry, and it has closed orbits because those closed orbits have to be parameterized by some angle living on a circle. And now we have another possibility of how to think about the axis. So the axis would be just a set of points in the manifold such that this Koenig vector field vanishes. And by vanishes, I mean that it vanishes as a vector field, not just that its norm is zero. And for a regular axis, there's a number of quite nice properties which people have been studying in last decades. So those are taken from paper by Marsens and Novia. So one can show that if the axis is regular, meaning those points where this cyclic Koenig vector field vanishes, if they are a regular part of the manifold, then of the spacetime manifold, then the axis actually creates a two-dimensional submanifold. It's, for example, it's time-oriented, it's autoparallel. They derive some nice geometric description of how to speak about tangent and normal vectors, how to identify them. And the two most important properties that I will generalize in this talk is the fact that cyclic Killing vector field close to the axis is space-like. And this is quite nice because now, if we know that this is true, then it's enough to look for points where the square of the Killing vector field vanishes. So instead of speaking about the Killing vector field itself, we just look at the normal and look for points where this is 0. And the second condition is the so-called elementarily flatness condition, which assures us that that this cyclic Killing vector field is 2π periodic. So by 2π periodic is the condition that we need for it to be for the axis to be regular. So to arrive at this condition, what you basically do is you expand the square of the cyclic Killing vector field. You expand the norm of its gradient. Because everything is regular, you can then evaluate this particular combination on the axis. And if C is 2π periodic in your spacetime, then this combination is 1 at the axis, which is regular. So this is the thing that we also trying to generalize. So this is the regular axis. There's also somehow related notion of a conical singularity. So what exactly is conical singularity? Usually the way it's done is that the way it's described is that the conical singularity is created when we have a wrong choice of the angular coordinate, such that the orbits of C of the Killing vector field are not parameterized to be 2π periodic. And also the picture that people usually show is that you take a piece of paper, you cut out a wedge of this piece of paper, and then glue the places you cut, which gives you some kind of a cone. So this is like a two-dimensional intuition about this thing. So of course, if you have such cone, then there is no possibility of associating to the cone any tangent space. There's no possibility of defining at the tip of the cone any differentiable structure. So it should be some kind of a singularity. And in fact, it has been shown that, for example, in Taub-NAT, the conical singularity, the singularity of the axis, corresponds to the so-called quasi-regular singularity. The axes are quasi-regular points. What this means is that the axis, there is no curvature singularity as such, and even the curvature is regular in all parallelly propagated frames as we tend to the axis. However, still there are curves which terminate at the tip of the cone, which you could, I think, quite easily imagine that if your curve arrives at the tip of the cone, because there's no notion of the tangent space there is no unique way to continue this curve through the tip of the cone. So that's basically the intuition. And there's another popular notion which is called conicity. It's a quantity that measures the strength of this singularity. So again, it's easier to imagine on a two-dimensional surface. So it's calculated by the so-called circumference to the radius test. And what you do is you take a take your you take your axis, draw some circle around it. This circle has a length L naught. Then you take the geodesic radius from the axis to the circle, and you calculate this limit as you shrink the curve, shrink the circle around the axis, around the pole. So if everything is completely regular, then you'd like to reproduce what happens just for a circle on a plane. So for a circle on a plane, certainly this limit would be just 1 because we have divided by 2 pi already. So for regular axis, for regular axis, we would expect the conicity equal to 1. So this is a nice story in 2D. What happens in 4D is a little bit more complicated. And I don't think there is much consensus on what to do in 4 dimensions. So there are some traditions of what people have been doing to actually say something about conicity. And I think that this boils to all of those receipts for calculating conicity in the literature boil down to just to the procedure by which you have to choose some two-dimensional surface in your space-time and then apply this definition above. So usually when we are interested in conicity, we are also talking about some black hole solution, some spherical black hole solution. So then what usually happens is that you write the metric in spherical, like some kind of spherical coordinates. You neglect the non-angular part. And so you work with a pullback of the metric on the surface parameterized by only angles. And then you apply this procedure above. However, there are some questions which naturally come to mind. Probably the main question is, if you calculate the conicity on some two-dimensional surface in the space-time, does it depend on the choice of this surface? And it would be curious if it didn't. There's some other questions, so like to which exactly point of the axis are we calculating this limit? Well, because on a two-dimensional surface, the axis is a point. However, in space-time, the regular axis was two-dimensional surface. Does this limit depend on the curve taken? And actually, how do we even distinguish points on the axis if the axis is not a regular part of your manifold? Because, as I said, we have a singularity there. So I think we're quite surprised because it seems that there isn't in the literature any, or at least we weren't able to find any like universally useful definition of conicity. Everything that we have shown happened in some coordinates, in some specific choice of coordinates, which basically corresponds, choosing a coordinate would correspond to choosing this two-dimensional surface. So this was quite surprising because, well, conicity actually appears in some physics. So if you know of any definition of conicity that is will be something other than what I will present, then please let me know. If you use conicity in your scientific life and you calculate it, then also please let me know how do you do this. It would be very interesting to compare. So what I will propose is some extension of both singular axis and of conicity. So what are the assumptions that we'll have? So for which type of space-time this definition will be valid? So we'll definitely need, we'll work with stationary axially symmetric space-times, by which I mean that the space-time has at least two-dimensional abelian algebra of Killing vector fields, which I'll denote by gamma. And in this algebra, I assume that there exists at least one, I mean exactly one actually a King vector field, which is cyclic, so its orbits are closed, and that it's 2π periodic. 2π periodic, and by stationarity, I mean that there should in this algebra exist infinitely many time-like King vector fields, which I will be calling observers in this talk, and we have to just choose one of them. Of course, this has to be satisfied only in some region of the space-time. So some known examples would be, for example, the exterior region of the Kerr black hole, where we have certainly we have rotational symmetry, and we have a time-like King vector field if we are outside in the outside region. This works also. It would work also in Schwarzschild, where we have more symmetries. We just have to choose one of those. We would choose in Schwarzschild, we choose one time-like King vector field, and then one of the rotations. Assume that it's 2π periodic, and this would form gamma. So the regular axis point is, as I said, this basically restates everything that was already done. So this is just a point of the manifold where this King vector field C, cyclic King vector field, vanishes. And then from the elementary flatness condition, you could get this a little bit strangely looking condition. However, it follows from this limit. So it's what is here is the norm of this cyclic King vector field. Then you take a gradient, and then we again take the norm. And as we tend to the axis, because the axes are the points where the also the norm of C vanishes, because C is space-like, then it has to be 1. And this is the condition that we'll be trying to generalize. So we are not so lucky, and we don't have a regular axis point. Then we propose to define some kind of notion of singular axis. So what we would like to expect from this definition. So first of all, it should be really a singularity. So this axis point shouldn't lie on a regular boundary point, because if you lie just on a regular boundary point, that we just extend the space-time, and there wouldn't be any notion of singularity. And by the intuition that we got from what people have been calculating for tau naught, we assume that this X has to correspond to quasi-regular singularity, meaning that it has to be some kind of singularity, but we don't expect the axis, we don't expect the curvature singularity to coincide with the axis of rotation. So the question arises, where exactly are those singular axis points? So we need some kind of notion which would correspond some kind of boundary of the space-time, which would correspond to singular points. And the solution that we have chosen is the so-called B boundary. What I mean by that is that there's this long-standing notion in general relativity that singularities correspond to endpoints of curves which cannot be continued, cannot be extended. So if I'm traveling along some curve, then if I arrive at some boundary, either I can continue through it, and then would be the regular boundary point, or I cannot continue traveling on this curve, and then this would correspond to some kind of singularity. So a similar notion to B boundary is the so-called G boundary, so where we consider the endpoints of geodesics. However, in B boundary, we consider endpoints of any curve. And I won't this is probably the most technical part of this talk. However, I will just roughly sketch what is the B boundary, and we don't actually use it explicitly in any of our calculations. So, so we want to somehow identify the endpoints of non-extendable curves. So to do that, we pass from the bundle to the bundle of orthonormal frames on the manifold. So what is this bundle? Is the fiber above any point of the manifold in this bundle is just a set of all frames above this point. And actually, this is just a principal fiber bundle with a group structure, which is the Lorentz group. And so this whole construction is the idea of Schmidt, and he proposed a natural way how to introduce a Riemannian metric in this frame bundle. And the fact that this is a Riemannian metric actually solves a lot of our problems, because if it's Riemannian metric, then Riemannian metric can be used to induce a topological metric. By Riemannian metric, I mean Riemannian metric tensor. And by topological metric, I mean just some function which will return the distance between 2 points, because in Riemannian metric, for Riemannian metric, we just use geodesics. And so we have topological metric, and we can take the topological completion of this frame bundle. And then what he shows is that if we quotient this completion, so we pass from the bundle again to the manifold, we got obviously what we started with, we got the manifold. However, we also get these additional points, which are the so-called B boundary. And they represent the endpoints of curves which are incomplete in the manifold. So then we use this framework to define the singular axis point and the corresponding axial Killing vector field. However, we do this in tandem. We have to define them both simultaneously. So we say that if some Killing vector field from gamma, if its norm vanishes towards some singular axis point from the B boundary, then and if this condition is satisfied, and this condition is based on the elementary flatness condition, if this is satisfied, then we call such point singular axis point, and such Killing vector field we call the axial. So they have to be really defined as a pair, cannot separately define the axis and the axial Killing vector field. And here's a technical assumption that what could happen is that for some points in the B boundary, you could find multiple axial Killing vector fields, so multiple Killing vector fields which satisfy these two conditions. And if this would be the case, then this definition would have to be somehow refined even further to exclude those cases. So for now, we suspect that this is the case, that this relation is unique, and I will be working under this assumption.
Yeah. What's E?
D.
A is defined.
It's just exterior derivative. This is a gradient of a norm. Okay, so we have our axis point, we have the axial Killing vector field, and now comes the nice part about this construction. So if we have the axial Killing vector field and we know that it's from gamma, then it has to be it must be possible to express it as a combination of the cyclic Killing vector field and of a time-lag Killing vector field, which both live in gamma. And the coefficients of this decomposition we call the conicity and the time shift. So I will explain the names in a couple of slides. However, what I think is particularly nice about this approach is that usually when one has to calculate the conicity, then there's some choice of curves. You have to calculate the radius of this curve, calculate the circumference. There's some integration involved in this procedure. However, in this way, if you have the Koenig vector field, then you're done. Then you don't have to calculate anything more. It's just you just read off the coefficients, and that's how it works. So, what are the typical examples of this axial Koenig vector field? So, if there's no time shift, so those pictures are just the orbits of gamma. Gamma being spanned by C and T. If there's no time shift, then they just both the orbits of A and C they coincide, and the A is just goes with a different velocity along this curve, so just parameterized differently. However, what happens in generic case is that the axial Koenig vector field is no longer closed. Its orbits are no longer closed. Instead, it has some kind of spiraling behavior. This has some consequences. For example, if you would like to use some kind of definition that would be based on integrating the circumference and the radius of this curve, then it's fine, because the orbit of A without time shift is closed. So you at least know that the circumference could be calculated. However, if you would like to use the same approach for the case with time shift, then you'd have to calculate along the red curve, because this is the orbit of, along the green curve. This is the orbit of the axial Koenig vector field. However, this orbit is not closed. So what do you do? Good question. So one possibility is to take the length of as a circumference, the length of this orbit between points P1 and P2, where what you get is they are defined by two successive intersections with the orbit of the timeline Koenig vector field T, which of course happens only if the time shift is non-zero. So so this is certainly a possibility. However, this possibility has some unintended consequence. Namely, I have only assumed that C is unique, and about T, I have just said that pick any timeline Koenig vector field that you'd like, and this will be your observer. So naturally, what happens is that if you change the observer, if you change the red curve, this intersection would lie in some different point. So the green line and some other red curve would intersect in different point, meaning this distance between points P1 and P2 would also be different. So this leads to the problem that the conicity with time shift necessarily will have to be observer dependent. So you could actually easily state the transformation laws for these quantities. So if we take another observer, so this T tilde, which also comes from gamma, some combination of T without tilde and C, then you just could use T in the decomposition of the axial Koenig vector field, and you would get some other quantities which would mimic, which would be what we defined conicity and time shift by. So the coefficient of time-like observer would be T over C, and the coefficient of cyclic would be C. And those quantities, how they transform. I should maybe mention that this absolute value comes from the fact that these conditions do not actually define A uniquely. They defined A up to change of directions. so up to a sign. So we choose to incorporate this ambiguity into definition of conicity. And so those are conicities as measured by some observer t tilde in terms of what measures the observer with observer following the curve t. So the conclusion is that both of them are necessarily observer dependent because they explicitly depend on these parameters b and alpha, which say which observer we have chosen. And when this is the case, so if there's no time shift in if there's no time shift for some observer, then the time shift for any observer is also zero. This follows from this transformation. And if this is the case, then also this denominator is 1, and so the conicity is the same for an observer. So this is the left case. This is the left picture. And so in the spacetime that people usually consider black hole spacetime, the time shift, which causes the observer dependency, it comes from the NAT parameter. So it's the NAT parameter that causes the time shift. And I suspect that this is the reason why people haven't really discussed this before, because, well, the most widely studied black hole solutions are, of course, those without the NAT parameter. And without the NAT parameter, this doesn't happen. There is no observer dependency of the measured conicity. So the natural consequences of those transformation laws is the fact that there must exist observer such that if I measure the conicity capital C, this observer chosen by this equation, this observer wouldn't measure any conicity. So so you cannot any longer say that, or maybe shouldn't, that the conicity is some quantity associated with the spacetime. It is just what some observer measures. And so the other consequence is that if we have at least two parts of the axis, so if our axis points all fall into two categories, so which usually corresponds to parts of the axis which are covered by theta equal to 0 or theta equal to pi in some spherical coordinates, then you can calculate this conicity difference, can propose this conicity difference, and there's always an observer who doesn't measure the difference of conicities. So why this is important, maybe, is because if there is no conicity difference between two parts of the axis, then I would assume that you could always, by some global rescaling of the angular coordinate, get rid of the conicity. However, this is the case only for this one observer who doesn't measure the difference of conicities. So let me go through some examples on how does this construction work. First example will say us why those names have been chosen. So we take Minkowski spacetime in just cylindrical coordinates. So this is certainly flat and completely regular. And then we could introduce another set of coordinates, which is tau and curly phi. In those coordinates, we assume that we'd reglue the spacetime such that not this original phi is a periodic coordinate, but that this new curly phi is the angle. So basically what I'm saying is that d over d phi, this phi is now cyclic. And so this is what people usually call a spinning cosmic string. This is actually a tensionless spinning cosmic string. Tensionless meaning that it's basically a flat metric. So there shouldn't be anything that's pulling or creating this tension in the string. And this is the case in this case, this metric is certainly regular for all of the points apart from possibly rho equal to 0. So if there is an axis somewhere in the spacetime, it has to be at rho equal to 0. And in fact, all of the axis points have rho equal to 0. And for all of them, we have the same axial cleaning vector field, which is this guy. This is the justification of the names we have chosen. So in particular, the time shift is A, which is this the parameter that causes well, the shift of the time coordinate here. And the B plays the role of like a global rescaling of the angular coordinate. Yeah, so if you choose B equal to 1, then there's no conicity, but there's still time shift for this particular observer, which is defined by d over d tau. Yeah. So the name time shift comes from this transformation. So what happens is that you basically shift the time by some angle. So on this spiral, you reglue the points lying on different levels of the spiral created by this transformation. So this is the simplest case. Slightly more complicated is the so-called symmetric. This is an extension of a Schwarzschild solution, so it's still vacuum. However, we have this additional parameter which is called alpha. It's called the acceleration parameter is denoted by the letter alpha. And with alpha 0, we get Schwarzschild simply. So here there are two. All of the axis points come into two. They collapse into two classes. So the class for theta equal to 0 and theta equal to pi. And for those two axis parts, for theta equal to 0 and pi, we have two different axial cleaning vector fields. So plus corresponds to theta equal to 0 and minus for theta equal to pi. And so from this, you could just read off what is the conicity, is the B times P plus minus, where plus minus meaning that it's evaluated at the corresponding theta. And so you could use this overall change of this overall conicity, overall change of the range of the angular coordinate to regularize one of the parts of the axis. So they're theta equal to 0 or theta equal to pi. However, you could do this trick only with one part of the axis. And if you calculate the conicity difference, then you actually get something that is completely independent of any like fictitious parameters or any observer. This is just the parameters of the spacetime. And this for the symmetric. For the symmetric, the conicity, first of all, is independent of the observer. So this is probably the other reason why people haven't noticed that there is some observer dependency, because anybody studying the cosmic string, I mean, this is the very popular model for cosmic strings. So people use this metric where the observer dependency doesn't happen. And the other thing is that this difference of conicity is typically associated with the tension of this cosmic string. So this tension of the cosmic string is also independent of the observer. It's just something associated to the spacetime. So finally, after 45 minutes, there's not in this talk. So of course, the main motivation for this construction is what we have noticed that happens if you have the knot parameter in your spacetime. So what is the nuts Taub knot spacetime? This is another vacuum solutions of Einstein equations, similarly to the symmetric. It's also a generalization of the Schwarzschild. So if the knot parameter L vanishes, then this metric tensor goes just to Schwarzschild. However, there is a singularity at the axis in this metric. We have also introduced this another fictitious parameter S, which will determine which part of the axis is regular, or maybe both of them are singular. So again, we have two axial Killing vector fields for two axis parts. However, here there should be B probably here. Sorry, because there's B here. So here we have time shift, and as I mentioned, the time shift is proportional to the knot parameter. If the knot parameter is 0, then the time shift vanishes, and the observer dependency also vanishes. So you could choose this S parameter to regularize one part of the axis, meaning you could, for one part of the axis, you could set the time shift to 0 by choosing S minus plus 1. However, you could do this only with one part of the axis. The other part of the axis necessarily has some time shift. And even the difference of conicities has the explicit dependence on the TT and the T phi, which tell us which observer we have calculated those quantities with respect to. So this is the simplest case with the knot parameter, and very similar results with some additional functions appearing, however, qualitatively the same, follow for the accelerated Carnot ADS. And what's a little bit curious and what ties this whole talk to what I have been doing with Professor Lewandowski during my PhD is that what we have been doing is we constructed the Misner interpretation of the accelerated Carnot ADS. So in Misner interpretation, you have to assume that there's a periodic time coordinate. There's a periodic there's a Killing vector, this time-like Killing vector field which has closed orbits, and it was a difference for us which Killing vector fields we have chosen to have closed orbits, and it turns out that this is exactly the one that doesn't observe any difference in conicities. So actually, what has allowed us to do this construction of Misner interpretation for Carnot EDS was exactly the fact that the conicity depends on an observer. So it's always possible to find the observer for which this conicity difference vanishes. So let me finish by just one more example, which is slightly pathological, but it might explain why we have made some choices rather than other. So consider a cosmic string. However, it is now z-dependent, meaning that A and B are functions of z. This is, I don't assume any field equations because well, the conicity should be the conicity and the axis should be just a matter of geometry. Any field equation shouldn't be involved here. So we just assume a metric of this form. And again, the axis should be, all of the axis points should be at rho equal to 0. We assume that this phi is cyclic. So if A is 0, then only the B depends on Z. Then all of the, for different Z's, we get different Killing vector fields, and the conicity depends. The conicity is defined for just z0, for just some choice of this coordinate z. However, what ties all of them together is that all of those guys, all of those scaling vector fields, they vanish at rho equal to 0. So our first guess was that we could just use this as a definition, that the norm of this field would vanish, and because we had also the condition on the gradient, the norm of the norm of the gradient of the norm, which was the other condition. However, what happens in general is that if the time shift is also z-dependent, then this axial Killing vector field, it vanishes for rho equal to 0, but only for some chosen z. So only for some on this what we imagine to be axis, only for some for different points on this axis, we necessarily have different axial Killing vector fields, because at each point in general only one would vanish. So it's not possible to just live with this condition. And by this I mean that we define the axis not as something that would resemble some extension a two-dimensional manifold, but we just talk about the axis points. So yeah, hence the need to define axis points. So what? Okay, the conicity is observer dependent. Why do we care? We care because the conicity is a quantity which actually sometimes appears in physics. So for example, if you do black hole thermodynamics, if you calculate the first law of black hole thermodynamics for, let's say, tau naught, then there appears some kind of conicity there. But this conicity is necessarily observer. So for which observer do you calculate this? You do this thermodynamics. So there's a folk knowledge, like a common understanding that the conicity, or the difference of the conicity, measures the tension of a cosmic string, as I argued as was in the case of the symmetric. However, if the conicity and the conicity difference is observer dependent, then does it mean that the presence of the cosmic string is observer dependent? This certainly shouldn't be so. And finally, in Plebański-Demiański parameter, this Plebański-Demiański spacetime, the acceleration parameter was tied to the difference of conicities, and then it's interpreted as a acceleration of a black hole. However, this cannot really be extended to so easily extended to the cases with the NOT parameters. Yeah. Okay. So I think I can let you. I can end with this. Thank you.
I have a question related to the Plebański-Demiański solution.
Mm-hmm.
Another parameter which was not discussed here, which corresponds to the, okay, let me say it this way. That parameter corresponds to so-called dual mass.
Mm-hmm.
There is something which is called dual spatial momentum. This is roughly dipole, whatever it means, parameter. So it's a parameter times cosine theta.
Okay.
And I call this in previous millennium this charge, the Plebański-Demiański charge. And it corresponds to the somehow topological singularity on the axis.
Mm-hmm.
So you should try to understand in your language what happens with this particular solution, where this parameter is not zero.
Okay, thank you. This is an interesting thing to check. Thank you very much.
Yes.